How's it going, everyone? Welcome to the ninth drill of the spring 21 semester. Today we're going to be talking about transformations, and we're just going to pick up right where we left off last week. So as a reminder, we had that prestige data set, but the actual the row names are the occupations, and so just pipe that straight into as Tibble to make it a Tibble, and then pull those row names into a column called occupation so that that's a usable data. And then we're going to take out, we already know based on what we did last week that we got to take out those general managers and physicians. So filtering those out by saying not occupation in this in operator, as a reminder, like takes whatever's on the left hand side and searches within some vector on the right hand side. So this is looking for occupation in this list or this combined vector of general managers and physicians. But because I have this exclamation point in front, it's negated. So that's saying not occupation is in general managers or physicians, which is just a programmatic way of saying that filter the occupation is not in this list. And so we will run that to get our data frame, and we should have 100 observations of our 7 variables. The model that we're looking at, we're wanting to look at that at income as a function of the percentage of women in the field and the years of education. And when we look at those model assumptions, here, first looking at normality, our QQ plot isn't looking great. We've got these huge tails that diverge substantially at the ends. And then looking at the residuals, this is pretty obviously not a normal curve. We got this huge peak and super flat tails. And so then when we look at our constant variance, once again, these aren't looking great either. This pink line should, for the spread level plot, should fall along this dotted blue line. And over here on our studentized residuals versus fitted values plot, recall what we want to see is more or less kind of a rectangle of random noise here. But what we can see is that the residuals are small here. And then as you move further to the right, they spread out more and more. So you have kind of this conical shape in the residuals, which is not what you want. That tells you that you don't have constant variance, because here the variance is like this. And then as you move to the right, that variance gets bigger. So that's how you know that you don't have constant variance. So those assumptions aren't looking so hot. So what do we do? Well, we can we can try applying some transformations to this model. So let's first look and try to see why we're having problems. So I'm just going to select our 3 variables and look at our plots here. And what we see is that income and women are pretty skewed, but I can't emphasize this enough. One thing that so many people struggle with understanding is it's not about the univariate distribution of variables that go into the model. In other words, it's not innately a problem that income is skewed or that women is skewed. The problem is when you put them into the model, what are the residuals in the model what's skewed? And sometimes you can have skewed univariate distributions of your variables, but when you put them into the model, it kind of works out, and the residuals aren't skewed quite the same way. So in this case, it is clearly a problem because we've already done our model assumptions, and we see that, like, yep, we don't have constant variance, we don't have our linearity assumptions satisfied. So in this case, we do need to do something. So we could try transforming a variable or even multiple variables if we needed to satisfy those model assumptions. So you can start by eyeballing the data just like this. To take a guess at what transformation might be best to use. Here's a link that it is a real simple chart that I've used before, and here it's this image. Rather, I need to clear out my plots, and so it's this is this link Note that I have this note here, and I do this down below in the script as well. This won't run for you. I have a PNG file in my working directory called dists.png, which is this image. It's this link, and I just saved that image to my local directory just because I don't like dealing with, having to open up browsers and other pop-up windows and stuff when I'm trying to screen record. So just FYI, ignore this. This is literally just, if you control or command click on that link, you'll see this same picture in your browser. But my point is that when you look at this, you can see, if your data looks kind of like this, then you could try to reflect and do a square root transformation. If it looks like this, then you might do a square root transformation. If it looks kind of like this, you might do that log transformation. If it's super skewed, then, you might do the inverse. And so depending on whether it's a positive skew, like over on the left, or a negative skew over here on the right, keep in mind, just remember that the skew is the direction that the tail is pointing. So if you have a big peak over on the left side and the tail trails off and points to the right, then that is a positive skew because the tail points to the direction of the skew. Over here where we've got the big hump over on the right and the tail trailing off to the left down towards the negative numbers, that's a negative skew. So again, if you have a negative skew that looks like this, you might want to do, you need to reflect it and do a log transformation. Something like this, you're going to do log transformation. Anyway, Bill also had some suggestions and some charts in the lecture last week. If you regularly work with data that needs to be transformed, like Bill said, he often works with reaction times, you'll get to know which transformations work for the data that you use regularly. And so if you have a positive skew, these transformations, what they'll do is they'll push in the tail and pull out this end. If it's a negative skew, the other transformations will do the opposite. Then we would want to push in this tail and pull out this end to try to flatten out, or not flatten out, but more centralize that curve. Raising to the power between 0 and 1 is going to raising a power between 0 and will do basically the same thing, but the interpretation is a lot harder, and I'll explain what I mean. So what we're going to do here is we're going to do this Box-Cox transformation. And so what the Box-Cox transformation does is it looks at your model and tells you what is the best transformation for your model, for your data, with best transformation being defined as like the most normal. So if we put our model in here, before I run this, I want to explain this note. You can't have any 0 or negative values in your dependent variable when you're using this model Box-Cox function. If you have zeros or negatives, you have to add some sort of constant to make the minimum greater than 0. So if there was an unemployed where their income was 0, then we would need to add, at least $1, or at least, something to make it not 0. And so instead of it being just income regressed on women plus education, it would be income plus 1 regressed on women in education. Or if the minimum value of y, your outcome, was negative 75, then you could do y plus 76 regressed on x or whatever. And it doesn't have to be a minimum of exactly 1. It just has to be above 0. It cannot be 0 or negative, because you can't log transform zeros or negative numbers. That you'll run into errors. So if we run our model Box-Cox for this model that we've run, what it tells us is our best lambda is 0.51. So that's not really easy to interpret, though, and we'll see why in just a moment. But using the Box-Cox, that best lambda power transformation, and this related to that Tukey's ladder of powers, if your best lambda is 0.5, for instance, then a square root transformation is what will be the most normal. And if you raised it to the power of 0.33, that would be that cube root, x to the power of 1/3, et cetera, et cetera. So basically, all this lambda tells you is that the best transformation of income would be income raised to the power of 0.51 minus 1 over 0.51. But that's really, really uninterpretable. Like, how are you supposed to, if that's how you transform your income variable, and that's like your outcome variable is, income raised to the 0.51 power minus 1 over 0.51, how do you even really interpret that? So, the closest thing would be, as far as like at least having a, nice simple thing would be like if you did a square root transformation to be 0.50 instead of 0.51. And so at least then you wouldn't have to be, you could just do a square root of your income and not have to do income to the power of 0.51 minus 1 over 0.51 and do this weird transformation. You could at least make it more simple mathematically by doing a simple square root. But even if you do a square root, it's still going to be hard to interpret. It's not intuitive. And for the purposes of drill, I am more concerned with interpreting these things. But one thing that I want to point out is that you're not always going to be necessarily, it depends on your research, but you're not always necessarily going to be interested in interpreting your coefficients at all. Sometimes you literally only care about the directions and significance of patterns and things, and like you don't need to interpret, in an understandable, unit. And so if that's the case, transformations don't matter. And that's why Bill's talked about oftentimes psychologists really hate transformations when other fields use them all the time, because the other fields, like, they don't care about saying like, oh, well, this goes up by $5. They just care about saying like, yep, this makes this other thing go up. And like, a significant amount, but like the actual unit doesn't really matter. So if you're not interested in interpreting your coefficients and just looking at those patterns and such, or seeing does adding this other predictor significantly reduce error, but like I don't care about by how many dollars or whatever, then you don't have to have these things in there. So here we definitely want to spread out our lower values and bring in the higher values, and that's what powers between 0 and 1 do. Logs do it too, so we might transform by using log base 2, using the function log 2. So instead of just log in parentheses, it's log 2. And so a 1 unit increase in log 2 income represents doubling of the income. So when we apply that transformation and refit the model, so now all I'm doing is it's the same model, but I am, instead of it just being income regressed on women and education, it's log 2 income regressed on women and education. And instead of the model, this is now called mod log. It's our log transformed model. So now when we look at our log 2, our log transformed model, how do we interpret this? Well, so here where we have, this tells us, our predicted log 2 income for, 0 women and 0 education. But since log 2, and that for education, it predicts, for instance, that every 1 year of education had like this slope is 0.17 for a 1 unit increase in the outcome. But the 1 unit increase in the outcome, a 1 unit increase in a log 2 transformed variable, means that it's doubling. So if we take, since each additional year of education predicts a 0.17 unit increase in log to income, if we divide that 1 unit by the slope, this 0.17, we get 0.588. Or in other words, for every approximately every 6 years of additional education, income is expected to double. So I'm not going to try to repeat all that. I'm just going to give you, I encourage you, if you need to like pause the video, read through this a few times and then play with these numbers, do the math and figure out what I just said, because I understand. Like, that is hard to follow. It's not intuitive, but like, I hope that illustrates exactly why it's cumbersome and unappealing to some people to deal with transformations. Like, what do you mean I can't just directly interpret this? No, because you're not talking about a 1 unit increase in income anymore. It's not just, a year of education increases your income by X dollars. It's now all of a sudden you have to think in terms of like this doubling income, because that's your outcome variable. And so take a few minutes to mull on this and try to figure out exactly what it means, that exactly why approximately each 6 years of education doubles income, and how we come to that based on these coefficients. And if you're still struggling, feel free to reach out to me or Bill, and we'd be happy to explain it to you. But as a reminder, the best transformation might not be the most interpretable transformation. And what I mean by that is, like, best, again, operationally defined as the most normal. In this case, would be, that 0.51 Box-Cox power transformation. But at least here we're able to do some math and think about it and figure out how to interpret this in terms of like, oh, well, every 5.88 additional years of experience is expected to double income. If you're talking in this unit, good luck putting that in an English sentence that people can understand. That's my point. And so what is the most normal may not be the best if you're trying to interpret it. So you may take something that's like less than ideal because it's better for like your specific goals of being able to interpret things. So after you transform a variable, you have to recheck your model assumptions, which we did last week, and I'm not going to spend time on this week. Instead, I'm just going to tell you what it would show, which is that things look better, but there's still problems. So what do we have to do? Well, we could try to also do some sort of transformation to our women variable. If you recall, women was also skewed. And so we could try to do something there, but in this case, it doesn't particularly help. And then it would definitely make interpretation harder, because now you're interpreting two transformed variables. So it's not even like, well, this, X years of education, predicts doubling income. Instead, like, you would have to think of like X transformed years of income is predicted to have this relationship with, education, transformed, the relationship with transformed income. This is the whole transformation thing gets kind of hard to wrap your head around. It can get confusing. So, but point is, it doesn't help for this particular model. I mean, if you want to try it out for yourself, go ahead. But it doesn't help. Like, if you did that and then looked at your model assumptions, you'd still be running into some problems. And so if you have data and variables that can't be transformed to meet the assumptions, you might want to consider an analysis that doesn't use the general linear model and therefore doesn't need those same assumptions. But remember that the general linear model is pretty robust to the violations of normality and constant variance, so you don't necessarily need to run some fancy modeling just because your assumptions are a little bit off. You got a little bit of violated heteroscedasticity or whatever. Linearity is more concerning, but small violations shouldn't automatically just make you throw everything out. Also keep in mind, because there are things besides these, fancy schmancy high-speed low drag models that you could do if you have problems, say, with heteroscedasticity. That there are additional ways that you can model, still using the general linear model, but using, like one example off the top of my head is using robust standard error estimation. And so there's a way that you can do that, and like a separate way within R that you have to approach it. And that's, one thing that I had to do on my thesis, for example, because I had some problems with heteroscedasticity, but I just used heteroscedasticity robust standard errors and solved my problem, and then I didn't have to worry about it. So there are other things that you can do if they are violating these assumptions. Get advice from people in your research wheelhouse, whether you're in cognitive or whatever. Just find out kind of what's normative in your field. Especially like Bill said, he often uses reaction times to things. And so if you're in a field that often uses reaction times, chances are there are a lot of researchers before who have long extended discussions about the different ways of handling these skewed reaction times and such. Also, again, this is another thing that you won't have, and I do because it's in my working directory, but as Bill and I have both said, don't be overly critical of your data. Remember that real life data is messy. It's never like perfectly pretty. Here in Bill's class, he often gives you very pretty, nice, neat, small data sets that don't have a bunch of missing values, don't have a bunch of stuff that needs to be cleaned and computed and moved around. It's usually pretty simple, straightforward data sets, just to answer specific questions. But when you get into the real world, you're not going to ever have data sets quite that clean and pretty. And so, as Bill mentioned, and I've told a few of you, like, I constantly get people like, oh, what do I need to do because my data is significantly skewed? And I just want to remind you that all I'm doing here is I'm creating a table. I'm creating 25 distributions of 100. I'm randomly sampling 100 values from a normal distribution, and then I'll plot them all together. And when I do that, what you'll see is that all 25 of these distributions, they are drawn from perfectly normal distributions. And still, like, look at this, like down here at 24, 18, 8, 4, like, a lot of these don't look like what we would think if we said draw a normal distribution. You would probably not draw something that looks like 24 down here. So my point is that remember that even if it is actually from a perfectly normal distribution, your sample may not have that normal distribution. And so that's why, like, you don't need to necessarily worry just because your sample looks, like this or like this. It could still be from a normally distributed variable in the population. For now, we'll pretend that log2 income solves our problem, though, and meets our assumptions just for, grins and giggles. So I'm just going to hand wave everything else away, and we're going to say that. Like, cool, log2, the log2 transformation of our income solves our problems. So after you transform a variable, the relationships between your variables will change. So if last week when we did our case analyses to look for those unusual things, the outliers, residuals, leverage, etc., those things may be different now because we have a different relationship within our between our predictors and our outcome because we transformed one of them. And so if we redo our case analyses, in this case, I'm just going to do the influence plot so that we can get all of it all at once. We have our, again, as a reminder, our residuals are here on the Y, our leverage or hat values are on the X, and the circles are scaled by Cook's D. And so when we look at this, we have like these 3 points that we can see that are like way out. And what I want to point out is like this one is definitely concerning. Its residuals are way off. And it also has pretty substantially sized Cook's D. This one also has significantly like off residuals and a huge Cook's D, plus pretty high leverage. This one over here has really high leverage, but its residuals aren't off very far, and its Cook's D isn't too bad. And so, like, if we just select those 3 values and then click our finish, we see that's 51, 61, and 82. Now, if you had to take a guess, this one over here, 82, if you recall from last week, we had one particular thing that had very high leverage. It was an unusual combination of predictors, but the residuals weren't far off. It didn't mess up our model too much. It wasn't too far off. And that was our sewing machine operators. And so if we want to see, well, what is 51, 61, and 82, we slice those 3 rows, we see that those are newsboys, babysitters, and sewing machine operators. So that is, in fact, that same variable from last week, but with the untransformed. It's still, so that, in other words, it's still an unusual combination of predictors. We didn't change the predictors any. And so, but the newsboys and babysitters are these 2 that have, concerning residuals and huge Cook's D's. So we're going to take those out and rerun our model again. So now all I've done is I filtered out. So let me once again run through this. This is saying, we'll ignore the exclamation point for a second, and occupation, percent in percent, then this C, newsboys, babysitters. Piece by piece, the C, newsboys, babysitters simply makes a vector of values, and those values are newsboys and babysitters. This in operator says to take whatever's on the right hand side and look for it in whatever vectors on the left hand side. And in this case, we're saying occupation in the vector newsboys and babysitters. But because we start out with this exclamation point, it's not occupation in newsboys and babysitters, which could also be verbally read as occupation that's not in the list, newsboys and babysitters. In short, this filter takes out the newsboys and babysitters, and so now we have 98 observations instead of our original 100. Did not need to click that. And so now we can refit our model again, and we're going to have mod 2 or mod log 2 based on those 98 observations. And we could look at them this way and look at things, but I just wanted to quickly, like whenever I do model tables, I like this package called Stargazer. It's the same information. I just didn't want to confuse anybody. So if you don't have Stargazer or want to see like the basic summary, it's all here. But what we can see is that like our model 1, which is this first one, we have our slope of women, and these in parentheses are our standard errors. And then this is that second model. And so when we look at these together, we can see that we had 100 observations versus 98. Notice that our standard error has gone down. Our error's gone down, which means we've increased our patterns, but importantly, our patterns and significance are the same. The slopes don't change much, and the significance doesn't change. Like they're still, everything is still pretty well the same. So in that case, we're taking out these 2, the newsboys and babysitters. Taking those 2 out did increase our power quite a bit, and importantly, it didn't fundamentally change our interpretations of our models. So the last thing that we're going to show real quick is how to plot these things. So starting with using expand grid, this is just how we've done it before. Where we create a data frame. I call it plot DF, where we just take the average of education and then every value of women from 0 to 100%, and then we'll use our predict LM. And with predict LM, we want to use our mod log to predict. we want to use our mod log to get our coefficients to do the predictions. The new data that we want to use is this plot data. So in other words, we want to take, we have some slope of education and some slope of women. So if we plug into the model the 10.69 for education and 0 for women, what is the predicted outcome and the confidence interval? If we do the same average education, but with 1% women, with 2% women, with 3% women, with each one of these things, when we run it, what do we get? And the answer is, well, if we have 0 women and average education, then here is our predicted outcome. With 1% women, here's the predicted outcome, etc., etc. So once we C-bind all that together, we now have this plot data frame. And now with that plot data frame, we can put it all together. So if I just run these first 3 chunks and just our genome points, here we have our percentage of women on the x-axis and our log2 income on the y-axis. And then from that, and note that that's from just pulling the raw data from the data frame. And then for the geome ribbon and the geome line, instead we pull our information from this plot df. So for the geome ribbon, we want our x to equal women, our y to equal the fit, and then y min and max to equal the lower and upper. And then for our geome line, we just need x to equal women and y to equal fit. So if we run also with the ribbon, we get that ribbon that it pulls from our plot df. And then finally, when we run it all together, it'll also add in that line, also pulled from plot df. The very last thing that I'll show you, which you really don't need to know, but it could come in handy for you one day, is how to do the curvilinear plotting. And so if I take this exact same plot, but I'm going to put the raw income on the y-axis. So instead of using log2 income, I just use income on the y-axis, the raw income. But because the model for PredictLM has log transform stuff, fit, lower, and upper, all the plot df values, these values, are all transformed. And so what that means is that I have to untransform them somehow. But I have to untransform them in line, meaning like within ggplot, like untransform them. And since it's a log2 transformation, you accomplish that by raising 2 to the power of each of those variables. So in other words, like I said, this is copied and pasted. It's the exact same code as this. The only difference is we delete this log2. So it's just y equals income. And then here for fit, lower, and upper, we change it to 2 to the power of fit, 2 to the power of lower, 2 to the power of upper. And then here, same thing, 2 to the power of fit. So when we run that, now we have our income is the original raw units, but it allows us to plot a curvilinear line here. So that wraps up our drill for this week. If you have any questions, just let me know.